Two trains race side by side, their engines screaming as steel grinds against steel. Crowds along the track cheer wildly, watching the blur of motion as each locomotive inches ahead of the other, until, in an instant, the impossible happens. The two trains collide. Metal folds like paper. A fireball erupts into the twilight sky. Shock ripples through the crowd. Because what they just witnessed shouldn't be possible at all. The tracks, after all, were parallel lines that, by definition, can never meet. And yet, they did. That contradiction lies at the heart of one of humanity's oldest obsessions: the geometry of the universe. For thousands of years, mathematicians believed that parallel lines were eternal companions, destined to travel together forever without crossing. Until the 19th century, when a handful of thinkers shattered that sacred rule, and in doing so changed our entire understanding of reality itself. Their discovery was more than a mathematical curiosity. It was a gateway into something far stranger: the idea that space itself could bend, twist, or fold back upon itself, that the universe may not be flat and infinite, but curved and finite, perhaps even looping in ways we can barely imagine. And it all began with a single, unsettling question. What if two parallel lines could meet? After all, that question would echo across centuries, from the dusty halls of ancient Greece to the deepest observatories on Earth. It would guide minds like Euclid, Gauss, Riemann, and Einstein toward a single, breathtaking realization: that geometry is not just an abstract game of shapes. It's the hidden code of the cosmos. Fast forward to the present day. On December 27, 2024, a telescope in Chile spotted something equally unsettling: an asteroid roughly the size of a football field, designated 2024 YR4. If it strikes Earth in 2032, it could release energy hundreds of times greater than the Hiroshima blast. The discovery triggered a worldwide alert, the first activation of the United Nations Planetary Defense Protocol. For a brief moment, humanity stared at the sky in collective fear. And then came the question scientists always ask: what are the odds? According to data, the chances of impact are slim, around 1 to 2%. But the deeper question lingered: why do we keep finding ourselves on the brink of cosmic coincidence? Are we simply unlucky occupants of a fragile planet? Or are we misunderstanding the structure of the very universe that surrounds us? Because at its core, the story of the expanding universe, and of whether it's expanding into something, is not a story of space but of geometry. It's the story of how ancient mathematical puzzles became the foundation of modern cosmology. It's a journey that begins with a ghost, a 13th-century bishop named Robert Grosseteste, whose obsession with light led him to propose an expanding universe centuries before the Big Bang Theory. It continues through the trenches of World War I, where a Belgian priest named Georges Lemaitre would defy Einstein himself by suggesting that the cosmos was growing, not static. And it stretches all the way to today's physicists, who are still asking: if the universe is expanding, what is it expanding into? It sounds like a simple question, childlike even, but it's one that breaks our deepest intuitions. After all, if a balloon expands, it expands into the air around it. If a fire spreads, it consumes the space before it. But what about the universe, the totality of everything? What could possibly lie beyond everything? To find the answer, we'll have to step far beyond common sense. We'll explore universes that curve back on themselves, where light can loop endlessly and where a traveler might one day look up and see their own galaxy appearing again in the distant night sky. We'll meet mathematicians who risked their sanity to describe impossible spaces, and physicists who discovered that time itself can bend under the weight of gravity. This is the story of how geometry became destiny, of how one ancient postulate, that two parallel lines never meet, collapsed under the pressure of reality itself, and of how that collapse opened a window into the most profound mystery of all: the shape, size, and fate of the universe. Somewhere between the infinite and the impossible, we will search for the truth. Because if the universe is expanding, we must ask one final, unsettling question: into what? Part 1. The first warning. It began as a faint glimmer, just a cluster of pixels in a sea of black. At 2:14 a.m. local time, the Vera C. Rubin Observatory in northern Chile captured a moving object streaking through the constellation of Eridanus. At first, no one noticed. Automated sky surveys generate tens of thousands of similar detections every night. Stray satellites, cosmic dust, and harmless asteroids that glide silently through the solar system. But this one was different. Its orbital path didn't fit any known pattern. The software flagged it as potentially hazardous, triggering a priority alert to NASA's Center for Near-Earth Object Studies in California. Within minutes, telescopes across the world were redirected to confirm the signal. The new object was soon given a name, 2024 YR4, and a provisional classification. Apollo-type asteroid, roughly 120 meters across. Its orbit cut through the plane of Earth's trajectory in a way that made astronomers uneasy. On December 28th, as dawn broke over Pasadena, a small group of scientists gathered in a windowless control room at NASA's Jet Propulsion Laboratory. The mood was unusually tense. "We've got one that might cross our orbit in 2032, said Dr. Lina Guerrero, a planetary defense specialist. "If the current trajectory holds, it's going to be close. Too close." They ran the simulations again and again. Each time, the result was the same. An impact probability between 1.2 and 1.8%. Statistically small, but astronomically terrifying. Within hours, the news had leaked. A tweet from an amateur astronomer in Argentina read, "Looks like the Rubin team just found something with a 2032 intersection. 1% chance of impact. Hashtag 2024 year 4. That single post exploded across social media, igniting what would later be called the Great Sky Panic. Memes, conspiracy threads, and emergency impact maps flooded the internet. Some people began stockpiling food. Others mocked the hysteria. But for scientists, the fear wasn't hysteria, it was data. The discovery of 2024 YR4 represented more than a potential disaster. It was a reminder of how fragile our understanding of cosmic geometry really is. Every orbit, every path through space, follows invisible curves dictated by gravity. Curves that twist through a four-dimensional fabric we still don't fully understand. As Dr. Guerrero later remarked in an interview, "Every time we find something new up there, we're reminded that the universe doesn't just expand. It moves, it bends, it pulls. Space isn't static. It's alive." That same day, the United Nations Planetary Defense Coordination Office invoked an unprecedented measure, the Global Observation Protocol. For the first time in history, telescopes from 47 countries were synchronized to track a single object. The world, for a brief moment, looked up together. The news stormed by the end of the week. The asteroid had dominated every major network. CNN's headline blared, "A 120-meter visitor from the dark. Is Earth in danger?" The BBC asked, "Should we worry about 2024 YR4? And in Tokyo, NHK aired a special segment simply titled, "The Geometry of Doom." But beneath the fear-mongering, something fascinating emerged. Journalists began reaching out to mathematicians, cosmologists, and philosophers. The conversation shifted from the odds of impact to the deeper nature of what impact even means in an expanding universe. If the universe itself is stretching, they asked, does that change how objects move through it? Are trajectories like 2024 YR4s truly fixed, or are they embedded in a larger cosmic flow, one that might subtly shift with the expansion of space itself? Most astrophysicists agreed that the effect would be negligible on local scales, but some whispered otherwise. One particularly controversial interview came from Dr. Aidan Cole, a theoretical physicist at Cambridge. He suggested that subtle deviations in the asteroid's orbit might not be due to observational error at all. "We tend to think of motion as happening in space," Cole said. "But what if space itself moves around us? The asteroid isn't just falling through gravity. It's surfing on the expansion of the universe. We're watching geometry in motion." It was the kind of statement guaranteed to set the internet ablaze, and it did. Within days, Dr. Cole's quote had been remixed into thousands of viral videos, each more speculative than the last. Yet behind the noise, a quiet realization was taking shape. To truly understand whether an asteroid or anything moves through space or with space, we must first understand the geometry of the universe itself. And that geometry is far stranger than most people can imagine. A brief history of fear. Humanity has always looked at the sky with a mix of wonder and dread. From ancient comets mistaken for omens, to the Tunguska blast of 1908, to near misses like Apophis and Bennu, every generation has faced its own celestial warning. But unlike our ancestors, we now know that space is not an empty void. It's a fabric, flexible, elastic, and vast beyond comprehension. When Einstein published his general theory of relativity in 1915, he replaced Newton's invisible forces with a universe made of curves. Space and time weren't separate entities. They were one continuous surface. The path of every planet, every asteroid, even every photon of light, was not a straight line but a geodesic, a curve carved into the cosmic fabric by gravity itself. And in that realization lay the seed of today's paradox. If the universe is a surface that can stretch, twist, and fold, then perhaps there's no outside for it to expand into. Just as the surface of a balloon grows without ever expanding into the rubber inside, our universe could be expanding within itself. Yet, as scientists tracked 2024 YR4's trajectory, they began to notice something unsettling. The asteroid's motion didn't quite match predictions. It wasn't enough to suggest danger, just enough to raise eyebrows. Some observatories detected minute deviations, almost as if space itself were subtly tugging at the rock. A few dismissed it as an error in calibration. But to others, it hinted at something deeper, perhaps a sign that the expansion of the universe might not be perfectly uniform after all. The question reemerges by early January 2025. The media frenzy had cooled, but in the scientific community, a different kind of excitement simmered. 2024 YR4 became more than an asteroid. It became a symbol, a reminder that even small celestial rocks can expose cracks in our understanding of reality. At a press conference in Geneva, Dr. Guerrero stood before a sea of cameras. She didn't speak of panic or apocalypse. Instead, she asked a question that sounded strangely philosophical. If everything around us is expanding, what does it even mean for something to move? Her words echoed the same question that had haunted mathematicians since Euclid. What is the shape of the space we live in? And so, while the world watched the skies for danger, a new investigation quietly began. One that would trace the strange history of how humanity learned to measure the unmeasurable. It would lead from ancient Greece to modern relativity, from flat lines to warped spacetime, from a bishop's candlelit study to Einstein's equations. And ultimately, it would lead back to that most unsettling of all questions. If the universe is expanding, what is it expanding into? Part 2: The Bishop and the Birth of Light. Long before telescopes and satellites, before the first human eyes saw Earth from orbit, one man in medieval England sat in a candlelit study and tried to imagine creation itself. His name was Robert Grosseteste, a scholar, theologian, and Bishop of Lincoln. To most of his contemporaries, he was a restless churchman, stern, reformist, and dangerously curious. But to a small circle of students at Oxford, he was something else entirely, the first true scientist of the Western world. In an age when knowledge was chained to scripture, Grosseteste sought the patterns behind divine design. He believed that by understanding light, one could understand God's mind. Because to him, light was not merely illumination, it was the substance from which everything was made. Around the year 1225, Grosseteste wrote a small, dense treatise in Latin titled De Luce, on light. It began with a single, radical line: "The first corporeal form which bodies have is light." According to Grosseteste, the universe began not with chaos, but with radiance. Light burst from a single point and spread outward in all directions, expanding space itself as it went. As this divine radiance stretched, it drew matter outward with it, thinning and cooling until the outer edges crystallized into the firmament, the heavens themselves. The image was astonishingly modern, an early vision of cosmic expansion, written 7 centuries before the Big Bang. Today, physicists might call it poetic speculation. But in 13th century Europe, it was heresy flirting with brilliance. The Church saw creation as instantaneous, perfect, and complete. Grosseteste dared to suggest it unfolded over time, that the universe grew. When historians rediscovered Deleuze in the 20th century, they were stunned. One line in particular seemed to echo the equations that Georges Lemaitre, the Belgian priest and physicist, would later use to describe the expanding cosmos. From that point of light, all things came into being. Lemaitre would call it the primeval atom. Grosseteste had called it lux prima, the first light. A rebel in robes, Grosseteste's curiosity did not endear him to power. He clashed often with both King Henry III and Pope Innocent IV, denouncing the corruption of the Church in letters so fiery that some scholars believe they hastened the Pope's death. Legend even claimed that the bishop's ghost returned to exact vengeance on the pontiff, an act that ensured Grosseteste would never be canonized as a saint. But his true rebellion was intellectual. Grosseteste insisted that faith must bow to evidence. He was among the first thinkers to advocate for experiment, to test, to observe, to measure. He dissected rainbows, studying how sunlight bent through drops of water, and correctly identified refraction as their cause. To him, rainbows weren't miracles, they were mathematics made visible. Nature is the handwriting of God, he once wrote, and light is the ink with which he writes. That idea that the universe is both divine and measurable became the seed of modern science. It bridged theology and physics, mysticism and method. Yet for all his insight, Grosseteste could not have known that his vision of expanding light would one day be more than metaphor. He imagined the cosmos as a finite sphere of creation. We now know it to be a boundless continuum. But the underlying notion that the universe had a beginning, that it grows, that light and matter are entwined, was centuries ahead of its time. From Grosseteste to the cosmos 700 years later, a young Belgian priest named Georges Lemaitre would pick up the thread. It was 1927, and Lemaitre had just finished calculating solutions to Einstein's field equations of general relativity. His result was shocking. According to the math, the universe wasn't static. It was expanding. When he presented his findings to Einstein himself, the great physicist frowned. "Your calculations are correct," Einstein said, "but your physics is abominable." Einstein believed the universe must be eternal and unchanging. To preserve that vision, he introduced what he called the cosmological constant, a mathematical trick that kept his universe balanced and motionless. Lemaitre, however, saw motion in the mathematics. Space itself was stretching and galaxies were drifting apart, not because they were moving through space, but because the space between them was growing. He imagined this expansion beginning from a single point, a cosmic egg exploding at the moment of creation. It was the same vision Grosseteste had described centuries before, light expanding into form. At the time, few took Lemaitre seriously. The idea of an expanding universe seemed absurd, even offensive. If space could grow, then time must have had a beginning, and that sounded uncomfortably like Genesis. But proof was coming. In 1929, the American astronomer Edwin Hubble used redshift measurements to show that distant galaxies were receding from us. The further away they were, the faster they moved. It was as if the cosmos itself was stretching, just as Lemaitre had predicted. Einstein later admitted his error, calling the cosmological constant the greatest blunder of my life. And so, Grosseteste's vision of expanding light, dismissed as mystical metaphor, was reborn as physics. Light as memory even today. Light remains our messenger from the past. When we look at the stars, we are not seeing them as they are, but as they were. Every photon is a time capsule, a ripple of the universe's earliest moments stretched thin by the expansion of space. The deeper we look, the further back we see, until eventually we reach a faint glow known as the cosmic microwave background, the fossil light from just 380,000 years after the Big Bang. It is, in a sense, Grosseteste's lux prima, still echoing through eternity. And within that ancient light lies another puzzle. The universe appears to be almost perfectly uniform, yet not quite. There are tiny variations, imperfections, that would later give birth to galaxies, stars, and planets. Without them, nothing would exist. To modern physicists, those fluctuations are the fingerprints of cosmic inflation. A brief, violent moment when the universe expanded faster than light itself. But to Grosseteste, they might have looked like something else. Divine texture. A pattern in the glow of creation. A legacy of geometry. If Grosseteste were alive today, he might be astonished to learn that his light of creation is now described by equations that span both mathematics and metaphysics. His intuition that geometry governs reality laid the groundwork for everything from optics to cosmology. It was he who first linked the curvature of light with the shape of the heavens, a connection that would later lead to Einstein's realization that gravity is curvature itself. In that sense, Grosseteste's candlelit vision never truly faded. It evolved. From medieval cathedrals to particle accelerators, from stained glass to quantum fields, humanity's quest has always been the same: to trace the geometry of light, and through it, the shape of existence. And if Grosseteste's words still resonate today, it's because they remind us that every scientific discovery begins as a spark of imagination, a flicker in the darkness that says, "What if?" From that point of light, he wrote, all things came into being, and so they did. Part 3, The Reluctant Genius. Einstein's Static Universe. It is 1917. Europe is still trembling from the Great War, and a 38-year-old Albert Einstein sits alone in his study in Berlin, staring at a page filled with equations that threatened to rewrite everything humanity thought it knew about reality. 2 years earlier, he had published his General Theory of Relativity, a work that merged space and time into a single four-dimensional fabric spacetime that curves in response to matter and energy. It was elegant, revolutionary, and terrifyingly vast. And yet, Einstein couldn't shake a single uncomfortable detail. His equations refused to sit still. According to the math, the universe could not be static. The fabric of spacetime, his own creation, seemed destined either to expand endlessly or collapse in upon itself. That couldn't be right, he thought. The universe, as far as anyone could tell, was eternal and unchanging. The stars had always been there. The sky was constant. Everything around him suggested stability, not movement. But the mathematics disagreed. The constant that wasn't to fix the problem. Einstein reached for a tool that has since become infamous. The cosmological constant, denoted by the Greek letter lambda. This extra term, added by hand into his field equations, acted like a kind of invisible pressure, a cosmic counterweight. It was a way to balance the equations so that gravity's inward pull could be perfectly offset by a gentle outward push. The result? A perfectly static, eternal universe. He was satisfied, or at least he convinced himself to be. Einstein later described the cosmological constant as necessary for the universe to remain of constant size. In essence, he had tamed his own theory, forcing it to align with common sense and the worldview of the early 20th century. But as history would show, the universe was under no obligation to obey common sense. A universe in motion just 2 years before Einstein introduced lambda, an obscure astronomer in Arizona had made an odd discovery. His name was Vesto Melvin Slipher, and he had been photographing galaxies, then called spiral nebulae, through a spectrograph that split their light into bands of color. What Slipher found defied expectation. Most of those galaxies' light was shifted toward the red end of the spectrum, a sign that they were moving away from us. He didn't know what it meant, but he had, unknowingly, uncovered the first evidence that the universe was not static at all. It was expanding. At the time, his findings drew little attention. The world was preoccupied with war, and even within astronomy, the notion that those faint spirals were other galaxies, vast islands of stars beyond the Milky Way, was still controversial. But one young astronomer, working quietly at the Mount Wilson Observatory in California, took note. His name was Edwin Hubble. The law of recession in 1929, after a decade of painstaking measurements using the world's most powerful telescope, Hubble published the result that would change everything. He showed that the farther away a galaxy was, the faster it appeared to be receding. Distance and velocity were linked in a simple linear relationship, what would come to be known as Hubble's law. The universe wasn't static. It was expanding. Einstein's elegant fix, the cosmological constant, was suddenly unnecessary. The cosmos didn't need a mathematical crutch to remain still. It wasn't still to begin with. When Einstein met Hubble in California a year later and reviewed the evidence for himself, he reportedly sighed, rubbed his forehead, and said quietly, "Then I suppose lambda was the greatest blunder of my life." Yet that so-called blunder would refuse to die. Decades later, lambda would return in a new form, as dark energy, the mysterious force driving the universe's expansion faster and faster. The geometry of reality. Einstein's mistake wasn't in the math. It was in the assumption. He had trusted intuition over geometry. To him, the idea of a changing universe felt absurd. But geometry, pure, unyielding geometry, told another story. His own equations described spacetime as something flexible, not fixed, and that flexibility meant that the universe could curve. It could stretch. It could grow. The man who had redefined gravity as the curvature of spacetime had, for a time, refused to believe that spacetime itself could move. But once he accepted it, the implications were staggering. An expanding universe meant that at some point in the past, everything, every star, every atom, every photon, had been closer together. Rewind the clock far enough, and all of space and time would collapse into a single point, a cosmic origin. For the first time, science had a plausible beginning for the universe. The doubt of a genius still, Einstein was uneasy. When Georges Lemaitre, the Belgian priest who had developed the expanding universe model independently, met him in 1927 to present his findings, Einstein's response was blunt. "Your calculations are correct, but your physics is abominable." He wasn't being cruel. He was afraid. The notion of a universe with a beginning felt too much like theology, too much like creation. Einstein's universe was supposed to be eternal, a stage on which the laws of physics played forever. But reality didn't care about philosophical comfort. Within a few short years, Lemaitre's model gained traction. Observations by Hubble, combined with Slipher's redshifts, confirmed the cosmic expansion. Einstein would eventually concede, praising Lemaitre's vision as the most beautiful and satisfactory explanation of creation to which I have ever listened. And in that moment, the reluctant genius bowed to geometry. The expanding fabric to visualize the expanding universe. Physicists began using analogies. Raisins in dough, dots on a balloon, coins on a stretching sheet of rubber. Each was imperfect, but they conveyed a crucial idea. The galaxies weren't flying through space. The space between them was stretching. The universe wasn't expanding into anything. It was simply expanding. This distinction baffled even seasoned scientists. People wanted to know where the Big Bang had happened, at what point in the sky the explosion had begun. But as Einstein and Lemaitre both explained, there was no center. If you could see the whole universe, you'd find expansion everywhere, equally. Every observer, in every galaxy, would see other galaxies racing away from them. Each would believe they stood at the center, though none truly did. It was a humbling realization, one that dethroned humanity not just from the center of the solar system, but from the center of reality itself. The endless question, and yet, one mystery still loomed. If the universe is expanding, what is it expanding into? Einstein's equations offered no external backdrop, no higher dimensional void. Space itself was all there was. The universe didn't need to expand into anything because space wasn't moving through something. It was creating more of itself. But the human mind resists such abstractions. We live in a world of boundaries, of inside and outside. Even Einstein, master of abstract thought, once admitted, it is difficult to picture space without anything outside it. Yet that is what our mathematics tells us. That mathematics would become the foundation of modern cosmology. A framework so strange that it would take generations to fully grasp. It would lead to the discovery of curved universes, warped geometries, and higher dimensions, ideas that would push even Einstein's intellect to its limit. And so, from Grost's candlelight to Einstein's chalkboard, one question endured, quietly glowing beneath the equations. If space can bend, can it also fold back upon itself? That question would haunt the next wave of physicists, mathematicians and dreamers who dared to imagine universes with no edge, no outside, and no center. Among them were two men whose names would come to define the very geometry of spacetime itself, Hermann Minkowski and Wilhelm de Sitter. Their work would not only reshape Einstein's theory, it would decide the fate of the cosmos. Part 4: The Architects of Curvature. Minkowski and de Sitter. The moon hangs in eternal silence, its surface carved with scars that have endured for billions of years. As you soar above its desolate plains, you begin to notice something strange about the names etched across that lunar landscape. Crater after crater bears the marks of the greatest minds who ever tried to understand the cosmos. Einstein, Hubble, Lemaitre, Slipher, and then two more separated by thousands of kilometers of lunar dust, yet forever linked by a deeper symmetry. One lies near the northern nearside, the other far to the southern farside. Their names, Minkowski and de Sitter. Their craters face away from one another, just as their ideas once did. Yet together they shaped the geometry of the universe. The professor and the judge's son Hermann Minkowski was born in 1864, a mathematical prodigy from East Prussia. He was the kind of man who saw equations as poetry, abstract patterns that whispered truths too deep for language. When he became a professor, one of his students was a young Albert Einstein. But Minkowski was not impressed. "He is a lazy dog," he once grumbled, frustrated by the young physicist's indifference to rigorous mathematics. Ironically, it would be Minkowski who gave Einstein's theory its most enduring form. In 1908, he unveiled a revolutionary idea. Space and time are not separate. They are fused into a single four-dimensional continuum, spacetime. From now on, Minkowski declared, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. It was a statement that rippled through physics like a thunderclap. Einstein initially dismissed it as unnecessary abstraction, but within a few years, he realized that Minkowski's geometric framework was precisely what his own theory of general relativity needed. Through Minkowski's lens, gravity was no longer a force but a curve, a bending of spacetime itself. And in that bending, the universe began to take on shape. Half a world away, another man was reaching for that same truth from an entirely different direction. Willem de Sitter, born in the Netherlands in 1872, was the son of a judge, a lineage of law stretching back generations. But where his family sought justice, de Sitter sought order in the stars. His mathematical temperament made him an ideal collaborator for Einstein. While Einstein provided the physical intuition, de Sitter supplied the geometric discipline. In 1917, the same year Einstein proposed his static universe, de Sitter unveiled a startling counterpoint, a dynamic solution to the field equations, one in which the universe expanded even without matter. It was empty space itself, de Sitter argued, that could stretch and curve. Gravity wasn't just about mass, it was about the shape of the vacuum. Einstein was skeptical. The two men debated fiercely, trading equations and essays across Europe, but their intellectual rivalry gave birth to two complementary visions of the cosmos: Minkowski's flat spacetime and de Sitter's curved spacetime. The question that followed would divide cosmology for decades. Which one describes the universe we live in? When straight lines meet again to visualize their difference, imagine standing on the surface of a vast sphere, the moon, say, and trying to draw a triangle. You begin at the North Pole, walk straight down to the equator, turn 90 degrees, and then trace another path back toward your starting point. You've just drawn a triangle with 3 right angles, a total of 270 degrees. That shouldn't be possible. In ordinary, flat geometry, triangles always add up to 180 degrees. But on a curved surface, the rules change. Lines that begin parallel, like lines of longitude, can meet again at the poles. This is non-Euclidean geometry, the kind that Minkowski and de Sitter helped bring to physics. In Minkowski's flat universe, the angles in a cosmic triangle always add up to 180 degrees. Parallel lines stay forever apart. Space behaves like an infinite plane, steady, uncurved, eternal. In de Sitter's universe, space is positively curved, like the surface of a sphere. Travel far enough in one direction, and you might return to where you began. Light itself could loop around the cosmos. There was even a third possibility, an anti-de Sitter universe, negatively curved like a saddle. In this strange geometry, parallel lines diverge faster and triangles contain less than 180 degrees. 3 possible shapes. 3 possible destinies. The universe could be flat, closed, or open, each with consequences so profound they bordered on metaphysical. The cosmic triangle to test which shape our universe truly had. Astronomers needed a way to measure cosmic triangles on the largest possible scale. They couldn't fly across galaxies to trace them, but they could use light. The universe's oldest light, the cosmic microwave background, CMB, became their ruler. When scientists mapped its faint, mottled glow, relic radiation from just after the Big Bang, they found patterns, tiny fluctuations in temperature. If space were positively curved, those patterns would appear larger. If negatively curved, smaller. What they found instead was extraordinary. The sizes matched the predictions for a flat universe. After billions of years of cosmic evolution, it seemed the universe had settled into Minkowski's domain, not de Sitter's. But it wasn't that simple. Einstein's equations allowed for subtle interplay between matter, energy, and curvature. The universe might appear flat locally while still curving globally, much like the Earth's surface seems flat to someone standing on a field. And beyond the observable horizon, beyond what any telescope could see, there could still be curvature, folded dimensions, or even loops of space where light meets itself again. The Garden of Geometry. When Minkowski died suddenly in 1909, his friend David Hilbert mourned him with words that perfectly captured their shared passion. It seemed to us a garden full of flowers. In it, we enjoyed looking for hidden pathways and discovered many a new perspective that appealed to our sense of beauty. And when one of us showed it to the other and we marveled over it together, our joy was complete. For de Sitter, that same garden would become his life's work. He spent his final years refining cosmological models, showing that the expansion of the universe could proceed even in the absence of matter, driven purely by the curvature of space itself. Today, his name lives on in the concept of de Sitter space, a mathematical model used to describe universes dominated by dark energy, universes that expand forever, accelerating as they go. Minkowski's flat spacetime remains the bedrock of relativity, the simplest, purest description of reality. De Sitter's curved spacetime is its haunting counterpart, a geometry of endless expansion. Together, they form the 2 pillars of modern cosmology, the geometry of stillness and the geometry of motion. The hidden shape of everything, every measurement we make of the universe, every beam of light, every gravitational wave, travels through this invisible architecture. It decides whether the cosmos will one day collapse back into itself, coast forever into emptiness, or expand until even atoms fall apart. But geometry, as both men understood, is not just mathematics. It is philosophy written in equations. Because hidden within these shapes lies a deeper question, one that haunted both Minkowski and de Sitter in their final years. If space can curve, does it end somewhere? Or does it fold forever upon itself? That question remains open. Every new telescope, every probe launched into the void, is a small step toward the answer. And as we continue this search, we inherit the legacy of those 2 names carved into the moon, one on the near side, one on the far. 2 men who gazed into the same dark sky and found, in its silence, 2 different geometries of eternity. Part 5, The Experiment of Infinity. Measuring the shape of the cosmos, the early universe glowed. Not with stars, not yet, but with something more fundamental, pure light, stretched thin across an infant cosmos. That ancient light still exists today, washing over us from every direction. We call it the cosmic microwave background, the afterglow of creation. To the naked eye, it's invisible. To the instruments aboard satellites like COBE, WMAP, and Planck, it is the faint whisper of the universe's first breath. and hidden in that whisper is geometry. When scientists mapped the cosmic microwave background (CMB) in exquisite detail, they found tiny, almost imperceptible variations in temperature, spots just a few millionths of a degree warmer or cooler than their surroundings. At first, these fluctuations seemed random. But when astronomers analyzed their scale and distribution, a stunning pattern emerged. They were exactly the right size to suggest that space itself is flat. Flat, not in the everyday sense of a tabletop or sheet of paper, but in the precise mathematical way Minkowski had defined it. A flat universe means that Euclid's ancient rules still hold true at cosmic scales. Parallel lines never meet, triangles sum to 180 degrees, and light travels in straight geodesics unless bent by matter. It was one of the most humbling realizations in modern cosmology. The universe, spanning billions of light years, filled with unimaginable energies, behaves as though it were drawn on an infinite sheet of geometric perfection. But that conclusion came with an unsettling caveat. The observer's horizon. When cosmologists say the universe is flat, what they truly mean is that the observable universe, the part we can see, is flat. Beyond that horizon, we cannot know. Light hasn't had enough time since the Big Bang to reach us from those distant regions, so we are blind to what lies beyond. Imagine standing on a calm ocean. The water around you looks flat, but you can't see the curvature of the Earth. The same is true of the cosmos. We may live within a small, apparently flat patch of a much larger curved reality. If that's true, then the universe could still be finite, looping back on itself in ways our instruments cannot yet detect. In such a universe, if you were to travel in a perfectly straight line, you might eventually return to your starting point, though you'd arrive billions of years later, seeing the Milky Way again from behind, its light having wrapped around the cosmos to greet you. Topologies of eternity. To test that idea, scientists turn to topology, the study of shape, not size. In mathematics, two shapes have the same topology if you can stretch or twist one into the other without cutting or tearing. A donut and a coffee mug, for example, share a topology because each has a single hole. Applied to the universe, topology asks, what happens if space itself has edges that connect? Imagine taking a square sheet of paper. Curl one pair of opposite edges together and glue them, you now have a cylinder. Then, bend the remaining edges around and join them as well. The result is a shape called a torus, a three-dimensional version of a donut. If our universe has this kind of topology, it could be finite but unbounded, limited in volume yet endless in experience. You could travel forever without finding an edge, only looping back through space itself. Astronomers have searched for evidence of this by looking for repeating patterns in the CMB, places where the same patch of primordial light appears twice in opposite directions, like mirrored images in a cosmic hall of mirrors. So far, none have been found, but the possibility remains tantalizing. Some models, such as the Hansch-Wendt manifold, suggest the universe could be folded in complex ways that would hide such repetitions from our view. In that case, we might already be seeing echoes of the same regions of space without realizing it. The flatness problem. Even as data pointed toward a flat cosmos, a new problem emerged, one so profound that it seemed to demand a rewriting of the universe's early history. If the universe began with the Big Bang, then any tiny initial curvature, positive or negative, should have amplified dramatically over billions of years. A slightly closed universe would have collapsed long ago. A slightly open one would have expanded too rapidly for galaxies to form. Yet somehow, the cosmos balanced on a knife's edge, so precisely flat that even minute deviations are invisible to our measurements. Why? To many cosmologists, the odds of this happening by chance were astronomically small. It was as if a pencil had been balanced on its tip for 13.8 billion years without falling. The solution, proposed in the early 1980s, was cosmic inflation, a brief, explosive burst of expansion in the first fraction of a second after the Big Bang. During inflation, the universe may have ballooned outward faster than light, not violating relativity, because space itself, not the objects within it, was expanding. This incredible growth would have stretched any initial curvature smooth, much like how blowing up a balloon makes its surface appear flatter and flatter the larger it gets. Inflation explained not only the universe's flatness but also the origin of those tiny ripples in the CMB. Quantum fluctuations, microscopic jitters in the early vacuum, were magnified to cosmic scales, seeding the structure of galaxies we see today. The illusion of infinity, but inflation came with its own strange implication. If it happened once, it might still be happening. In some versions of the theory, inflation never ends entirely. It continues in other regions of spacetime, spawning countless bubble universes, each with its own laws of physics. Ours would be just one among an infinite multiverse, separated by unreachable expanses of inflating void. In such a picture, asking what is the universe expanding into becomes almost meaningless. There may be no outer space, no boundary, only an eternal froth of creation, bubbling with universes that appear and vanish like sparks. Still, the question persists because it's human to ask where things go. We are creatures of motion and direction, and the idea of expansion without destination feels incomplete. Einstein himself wrestled with this. When journalists pressed him on what lay outside the universe, he once replied, "Nothing is outside. Space is not in space." It was a maddening answer, logically correct, emotionally unsatisfying. Even today, cosmologists admit that while mathematics describes how space expands, the why remains elusive. The map of the infinite every few years. As technology improves, humanity redraws its map of the cosmos. The Planck satellite, launched by the European Space Agency in 2009, provided our most detailed picture yet of the CMB. Its measurements refined the age of the universe, 13.8 billion years, and confirmed that on the largest scales, space appears astonishingly flat. But between those numbers lies something profound. If the universe is indeed infinite, then it's not expanding into anything at all. An infinite expanse cannot get bigger, because it already contains everything. The expansion we measure is the stretching of the distances within infinity, not a growth into some external void, but a change in the internal relationships of space itself. If the universe is finite, then its expansion could be curvature unfolding, a balloon growing in size, but with no outside surface to expand into. Just more geometry, more spacetime, more existence. Either way, the cosmos refuses to give us edges. The edge of knowledge. Astronomers often describe the observable universe as a sphere centered on us, about 93 billion light-years across. But that sphere isn't an object. It's a limit, a boundary not of space but of time. Beyond it lies the unseeable past, regions of spacetime forever out of reach. For all we know, the universe could twist, loop, or fold into dimensions we cannot perceive. In the end, we may never determine whether the cosmos is truly infinite or merely pretending to be. And perhaps that's the point. Because in searching for the edge of the universe, what we've really been doing is mapping the edge of understanding itself, an expanding frontier of curiosity, always one horizon beyond our reach. The universe may have no boundary, but knowledge, like space, expands into the unknown. Part 6, The Paradox of Curved Time. Riemann and the Hidden Dimensions. In the quiet of a German lecture hall in the summer of 1854. A shy young mathematician named Bernhard Riemann walked nervously to the front of the room. His audience was small but formidable. Professors, philosophers, and one elderly man whose approval he both feared and revered, Carl Friedrich Gauss, the most celebrated mathematician of his age. The title of Riemann's talk was unassuming, On the Hypotheses Which Lie at the Foundations of Geometry. But what he would say that day would change not just mathematics, but the very way humanity would one day picture the universe. The seeds of a new geometry. For 2,000 years, geometry had been Euclid's kingdom. His postulates, flat planes, straight lines, parallel rules, were the bedrock of reason itself. Yet there were whispers that his world was incomplete. A century earlier, Gauss himself had begun to doubt the universality of Euclid's flat geometry. While surveying the mountains of Hanover, he noticed that the rules of triangles drawn across vast distances didn't quite add up. The curvature of the Earth distorted them. That experience led Gauss to a profound insight. Geometry doesn't depend on where you draw it, but on the surface itself. He realized that you could describe curvature from within a surface without ever needing to step outside it. A sailor on a ship doesn't need to look at Earth from space to know it's round. The math of navigation already tells him so. In 1827, Gauss published this revelation in a paper with an unassuming Latin title, Theorema Egregium, the remarkable theorem. His core message was revolutionary. Curvature is an intrinsic property. You don't need an external dimension to measure it. You can live entirely within a surface and still know it is curved. It was a small step for geometry and a giant leap for the imagination. Riemann's leap into the abstract. Riemann took Gauss's insight and exploded it into higher dimensions. In his 1854 lecture, he asked a question that would echo for centuries. What if space itself, real physical space, has curvature? To most people, curved space sounded absurd. Space was empty, after all, a stage on which matter acted, not an actor itself. But Riemann argued that geometry could exist in any number of dimensions, curved or not, and that the rules of shape, distance, and direction would depend entirely on that curvature. He introduced the concept of the metric tensor, a mathematical object that defines how distance is measured in any curved space. It was as if he had built a ruler flexible enough to measure both the flat plane of a table and the curve of a globe. Gauss, listening quietly in the front row, was stunned. "This is truly extraordinary," he murmured to a colleague afterward. What Riemann had done, without knowing it, was lay the groundwork for the mathematics of spacetime, decades before Einstein would give it physical meaning. The hidden curvature of space. To grasp what Riemann meant, imagine an ant crawling on a stretched rubber balloon. The ant cannot see the balloon's roundness. It only knows the surface beneath its feet. If it draws a triangle large enough, the angles will add up to more than 180 degrees, revealing the balloon's curvature from within. Now imagine that same principle applied not to a balloon, but to the universe itself. Space might look flat to us, just as the ground looks flat to the ant, but on scales beyond our perception, it could be curved through dimensions we can't see. That idea, space bending without an outside, was the conceptual key Einstein would later use to describe gravity. But in Riemann's time, it was simply beautiful mathematics, abstract and hauntingly ahead of its age. The fourth dimension. In the decades that followed, mathematicians began to play with Riemann's ideas. They imagined shapes that twisted through 4, 5, or even 10 dimensions, objects that could exist logically, even if not physically. In art, literature, and philosophy, the fourth dimension became a symbol of transcendence. In science, it remained a riddle waiting for meaning. Then, in 1908, Hermann Minkowski, Einstein's former professor, provided that meaning. He united Riemann's multidimensional geometry with Einstein's theory of relativity and declared that space and time were inseparable. The universe was not a static, three-dimensional grid, but a four-dimensional manifold, a space-time continuum where every event, every particle, every photon had its coordinates. Curvature was no longer just an abstract idea, it became gravity itself. Matter told spacetime how to curve, and curved spacetime told matter how to move. This elegant reciprocity was Einstein's greatest triumph, and Riemann's greatest prophecy fulfilled. The intrinsic and the extrinsic. But Riemann's geometry also revealed a subtle, almost philosophical paradox. A surface, like a sphere, can be curved intrinsically without requiring any external dimension to hold it. You don't need to imagine the Earth floating in three-dimensional space to describe its roundness. The curvature exists within the surface itself. Likewise, our universe, no matter how it curves, does not need to bend into anything. This curvature is intrinsic. In other words, the universe does not need an outside to expand into. It curves within itself, its geometry self-contained and self-sufficient. It's a concept that feels alien to intuition but makes perfect sense to mathematics. Maps and distortions. To see this in action, look at a world map. Most of us grew up with the Mercator projection, a rectangular map that makes Greenland look nearly the size of Africa. In truth, Africa is 14 times larger. The distortion arises because you can't flatten a curved surface without stretching or compressing it. This simple fact that no map can perfectly represent a curved world was Riemann's insight made visible. And just as the surface of Earth defies perfect mapping, the universe defies perfect comprehension. Every measurement we make is a projection, a limited view of a vast, curved reality we inhabit but can never see in full. Beyond geometry, by the late 19th century, mathematicians were already exploring geometries that no longer required human intuition. Non-Euclidean had become a badge of the avant-garde, a frontier of thought that blurred the line between math and metaphysics. Yet Riemann himself remained modest. He spoke of his ideas as a mere hypothesis, a framework to think with rather than a final truth. He could never have imagined that his abstract equations would one day describe black holes, gravitational waves, and the birth of the universe. But his geometry made it all possible. Without Riemann, Einstein could not have curved spacetime. Without Gauss, Riemann could not have curved space. Without either, we might still think the universe was flat, eternal, and empty, the hidden dimension within. Even now, Riemann's ideas continue to echo in modern physics. When string theorists talk about curled-up dimensions or quantum gravity, they are using Riemann's language. When cosmologists describe the expanding universe as a four-dimensional hypersurface, they are walking the mathematical paths he first drew in that 1854 lecture hall. And so, more than a century before anyone asked, "What is the universe expanding into?" Riemann had already given the answer, into itself, because in his geometry, space does not need a boundary. It is both the container and the contained, both the question and its own answer. The infinite within. As Gauss watched Riemann conclude his talk that day, he was silent for a long time. Then he smiled, a rare expression for the old man, and said quietly, "This is a new way of thinking about space itself." Riemann's lecture would not be published until after his death. But when it was, it changed everything. From the curvature of a triangle to the curvature of the universe, geometry had revealed a profound truth. Reality does not require an edge. And as we trace that realization forward, from Riemann's chalkboard to Einstein's field equations, we begin to see that the question of expansion was never about where the universe is going. It was always about what the universe is. Part 7: The Fabric of Gravity. Einstein and the Shape of Spacetime. In 1915, in a small, paper-strewn office in Berlin, Albert Einstein was on the verge of collapse. For nearly a decade, he had been chasing a ghost, an invisible mechanism that could explain gravity not as a mysterious force, but as something geometric, something woven into the very fabric of existence. The journey had begun with an apple, or rather with the legend of one. Newton had called gravity a force of attraction acting at a distance. To Einstein, that explanation was no longer enough. What was this invisible hand that reached across empty space? How could it act instantly, with no signal, no medium, no delay? His intuition whispered that gravity wasn't a force at all. It was the shape of space. And to give that idea substance, he turned to the mathematics that Bernhard Riemann had created 60 years earlier. From acceleration to curvature, the breakthrough began with something deceptively simple: the equivalence principle. Einstein realized that gravity and acceleration felt the same. If you were sealed inside a spaceship far from any planet, you wouldn't know whether the pull you felt on your feet came from gravity or from the ship's engines accelerating upward. Drop a ball and it would fall just as it does on Earth. That insight led him to a profound conclusion. Gravity wasn't pulling things downward. Space itself was curving their paths. Objects in free fall weren't being forced to move. They were simply following the straightest possible routes through curved spacetime, geodesics, the very lines Riemann had described. The universe, Einstein realized, wasn't a stage on which events unfolded. The stage itself was part of the play. The equations of reality, but turning that intuition into mathematics nearly broke him. Einstein struggled to find equations that could describe how matter and energy shape the curvature of spacetime, and how that curvature, in turn, dictates the motion of matter. For years, he failed. He tried and discarded formulation after formulation, haunted by rivals like David Hilbert, who came dangerously close to solving the puzzle first. Finally, on November 25, 1915, Einstein stood before the Prussian Academy of Sciences and presented his final version, the field equations of general relativity. The bending of light. Einstein's theory made a bold prediction. Light itself should bend when passing near a massive object. Not because light had weight, but because spacetime around that mass was curved. To test it, astronomers needed an eclipse. Only during a total solar eclipse could they see distant starlight grazing past the edge of the sun. In 1919, the British astronomer Sir Arthur Eddington led 2 expeditions, one to Brazil and one to the island of Principe off the coast of Africa, to observe the May eclipse. When the results came in, they were astonishing. The starlight had shifted exactly as Einstein's equations predicted. "Lights all askew in the heavens," read the New York Times headline. Men of science more or less agog. Overnight, Einstein became a global icon, the first physicist to achieve the status of a celebrity. Yet behind the fame was something quieter, deeper. Humanity had finally confirmed that geometry itself could bend under the weight of existence. The fabric itself moves once gravity was geometry. An entirely new world of questions opened. If massive objects could warp spacetime, could they also ripple it? Einstein believed they could. He predicted the existence of gravitational waves, disturbances that travel through the cosmic fabric at the speed of light, stretching and compressing space as they pass. But the effect was minuscule, far beyond detection in his lifetime. For decades, gravitational waves remained a beautiful theory, unproven but tantalizing. Then, in 2015, exactly a century after Einstein's equations were published, the LIGO observatories in the United States detected the faint tremor of 2 black holes colliding over 1 billion light-years away. It was the sound of spacetime itself ringing like a drum. Einstein's fabric was alive. The shape of destiny. General relativity also transformed how scientists saw the universe as a whole. If gravity was curvature, then the cosmos could be curved too, its entire structure a vast four-dimensional manifold. Depending on its density, that manifold could be positively curved, closed like a sphere, flat, Euclidean, infinite, negatively curved, open like a saddle. Einstein initially hoped for a static, closed universe, one that neither expanded nor contracted. To make that possible, he inserted the cosmological constant, his infamous lambda, into the equations as a kind of repulsive pressure. But as Hubble's observations later proved, the universe was expanding, and Einstein would famously call lambda his greatest blunder. Yet that blunder would one day return as one of cosmology's greatest truths. Dark energy, the mysterious force that now drives the universe's accelerating expansion. Einstein, it turned out, had accidentally predicted the future. When space becomes time, one of general relativity's strangest consequences is that space and time are interchangeable aspects of the same continuum. Move fast enough and time slows down. Experience strong gravity and time itself dilates. Near the edge of a black hole, a region where spacetime curvature becomes infinite, time can effectively stop for an outside observer. The event horizon, that perfect one-way boundary, is not a wall but a distortion in geometry so extreme that even light cannot find its way out. When we look at a black hole, we are not seeing an object. We are seeing the limits of geometry itself. A universe made of geometry everywhere we look. Einstein's equations are written into reality. The orbit of Mercury, precessing exactly as predicted. The bending of light around galaxies, creating cosmic mirages called gravitational lenses. The ticking of GPS satellites, corrected for the warping of time by Earth's gravity so our navigation remains precise. Every device, every telescope, every probe is a small affirmation that the universe truly is a geometric being, dynamic, responsive, and alive. And if space can bend, stretch, and ripple, then the expansion of the universe is no longer mysterious. It is simply the evolution of geometry itself, the slow unfolding of a shape too vast for the human mind to visualize. The return of the constant. In the late 1990s, 2 teams of astronomers studying distant supernovae discovered that the universe's expansion was not slowing down. As expected, it was speeding up. Something, an unseen pressure, was pushing spacetime apart. The simplest explanation? Einstein's old lambda, the cosmological constant, was real after all. Today, we call that phenomenon dark energy, and it accounts for roughly 70% of the total energy of the cosmos. It is the modern reincarnation of Einstein's blunder, the quiet engine of expansion that keeps creating more space, more distance, more time. The universe, it seems, is still following his equations, just not in the way he expected. Geometry as existence. At the end of his life, Einstein would often sit by the window of his Princeton home, staring at the sunlight on the trees outside. He was no longer chasing fame or unification. He was simply contemplating the geometry he had uncovered. To a friend, he once wrote, "The most incomprehensible thing about the universe is that it is comprehensible." He had turned the poetry of Grostist's light of creation into mathematics. He had transformed Riemann's curved surfaces into the living fabric of reality. And in doing so, he had revealed that everything, matter, motion, and even time, is the unfolding of geometry itself. The universe isn't expanding into space. Space is what expansion is. Toward the horizon a century later, we still live inside Einstein's geometry. Our telescopes stretch toward the edge of the visible universe, where spacetime fades into the unknown. Beyond that horizon, the equations still hold, but our understanding falters. Is space truly infinite, or will it one day fold back upon itself? Is time an arrow or a loop? Einstein left those questions open, not as failures but as invitations. Because for him, the beauty of the universe lay not in its answers, but in the endless, expanding questions that geometry allows us to ask. Reality, he once said, is merely an illusion, albeit a very persistent one. And perhaps that illusion, woven from curved space and flowing time, is the closest we will ever come to touching the infinite. Part 8. The edge of spacetime. Black holes, wormholes, and the limits of geometry. Imagine a place where the universe folds in on itself, where time no longer flows forward but simply stops. A place where space curves so violently that every direction leads inward, toward nothing, toward everything. That place is called a black hole, and it is the most extreme expression of Einstein's geometry. When Einstein completed his field equations in 1915, he had no idea they contained monsters. He believed the cosmos was smooth, continuous, and elegant, too elegant to permit such absurdities. But within weeks, a young German physicist named Karl Schwarzschild, serving on the front lines of World War I, wrote to Einstein from the trenches with a startling discovery. He had found an exact solution to Einstein's equations, a description of spacetime around a perfectly spherical mass. The mathematics revealed a critical radius, where the curvature of space became infinite. Light itself could not escape beyond that boundary. Einstein dismissed it as a curiosity, a mere mathematical artifact. But decades later, it would become clear that Schwarzschild had glimpsed something real, a doorway at the edge of existence. The horizon of no return. A black hole begins simply enough with mass. Compress enough of it into a small enough region, and gravity overwhelms everything. The escape velocity, the speed required to break free, rises until it exceeds the speed of light. At that moment, space and time switch roles. The boundary where this happens is called the event horizon. Once crossed, all paths, all trajectories, all futures lead inward. To an outside observer, anything falling toward a black hole appears to slow, its motion frozen just above the horizon. Time itself dilates infinitely. But to the falling object, nothing unusual happens. It crosses the threshold and continues inward, toward what mathematics calls the singularity. A point of infinite density where the equations of physics collapse. No one knows what truly lies there. General relativity predicts a singularity, but quantum mechanics, our theory of the very small, refuses to allow infinities. Somewhere in that invisible heart, a deeper theory must emerge. The black hole, then, is not just an object. It is a boundary between what we understand and what we do not, a literal edge of spacetime and of knowledge. The geometry of shadows. For nearly half a century, black holes remained theoretical. Then, in the 1960s, astronomers began to find stars that behaved as though they were orbiting invisible companions. These unseen partners were so dense that only a black hole fit the data. In 2019, a global network of radio telescopes, the Event Horizon Telescope, finally captured the unseeable, the shadow of a black hole in the galaxy M87. The image was not a photograph of the hole itself, nothing can escape its gravity, but of light bent around it, the silhouette of spacetime distorted. What we saw was geometry made visible. Space twisted, time warped, light itself forced into orbit. Einstein's equations, written on paper a century earlier, had become an image on the world's screens. Wormholes, shortcuts through curvature if space can bend. Can it also fold? Mathematically, the answer is yes. Not long after Schwarzschild's discovery, other physicists noticed that Einstein's equations allowed a peculiar structure, a bridge connecting two regions of spacetime. In 1935, Einstein and his colleague Nathan Rosen formalized this idea in what became known as the Einstein-Rosen bridge, a theoretical tunnel linking two universes or two distant points in the same one. Later, physicist John Wheeler would give it a name that would capture imaginations for generations: the wormhole. A wormhole, if it exists, would be a tunnel through spacetime itself, a cosmic shortcut. Travel through it, and you might emerge not just light years away, but elsewhere in time. Science fiction embraced it instantly. From Interstellar to Stargate, wormholes became gateways to adventure, symbols of cosmic possibility. But reality remains far less forgiving. For a wormhole to stay open, it would require something that doesn't seem to exist: negative energy or exotic matter, capable of counteracting gravity's relentless collapse. Without it, any wormhole would snap shut faster than light could pass through. Still, physicists haven't given up. The mathematics of general relativity doesn't forbid them. It merely demands a universe far stranger than we can yet construct. The information paradox: the more we learned about black holes, the more paradoxes they spawned. In the 1970s, Stephen Hawking combined Einstein's theory with quantum mechanics and made a shocking prediction. Black holes aren't truly black. Quantum effects at the horizon should cause them to emit faint radiation, now called Hawking radiation, and eventually evaporate entirely. But this raised a terrifying question. If a black hole disappears, what happens to the information, the physical state of everything it consumed? Quantum theory insists that information can never be destroyed. It can be scrambled, but not erased. Einstein's geometry, however, suggested the opposite. Once matter crossed the event horizon, it was gone forever. This contradiction became one of modern physics' most profound mysteries: the black hole information paradox. Over decades, physicists have proposed daring resolutions. Information might be encoded on the horizon itself, or leak out in subtle correlations within the radiation. The current leading idea, holography, proposes that all the information inside a volume of space can be represented on its surface, just as a 3D image can be projected from a 2D hologram. If true, the universe might be a holographic projection of its own boundary, a cosmic illusion woven from geometry and information. Beyond the horizon, black holes are no longer just astronomical curiosities. They are laboratories for the deepest laws of nature. In their warped geometries, we glimpse clues about the union of the large and the small, the marriage of Einstein's smooth spacetime with the quantum granularity of matter. The frontier is now called quantum gravity, and its explorers believe that somewhere near the singularity lies the bridge between relativity and quantum mechanics. Some theories suggest spacetime itself is not continuous but made of discrete quanta, tiny loops or strings vibrating in higher dimensions. Others propose that geometry emerges from information, that spacetime is not fundamental at all, but a pattern born from the entanglement of quantum states. In that vision, gravity is not a force or even a field. It is an illusion of connectivity, the shape that information takes when viewed at cosmic scales. If that is true, then the universe may not be made of matter or energy or even space and time. It may be made of relations. The end of geometry for Einstein, this idea would have been both thrilling and terrifying. He saw in geometry a final refuge of certainty, the pure logic of curvature. But his equations, when taken to their limits, now seem to dissolve geometry itself. At the singularity, distances, directions, and durations lose meaning. The coordinates of space and time become meaningless. What remains is unknown, perhaps a new kind of order beyond geometry, beyond even physics. In that sense, black holes are the end of space not just physically but philosophically. They are the points where thought itself breaks down. Yet from that breakdown, new insight blooms. Hawking once wrote, "Black holes are not the eternal prisons they were once thought to be. Things can get out." He might have been speaking not only of matter but of understanding itself. Every paradox they create forces us to expand our definitions of reality, of existence, of possibility. The mirror of infinity, when we look into the shadow of a black hole, we are seeing the universe look back at itself. In that abyss, we find the same question that haunted Grostist's candlelight, Riemann's chalk, and Einstein's equations. If the universe has no outside, where do its boundaries lead? A black hole answers, inward. It folds space until the inside becomes the outside, until direction loses meaning and expansion becomes collapse. And yet, through that collapse, the universe may be creating again. Some physicists now suspect that black holes could spawn new universes on the other side of their singularities, each a child cosmos with its own laws of physics. In that possibility, the cycle of creation and curvature becomes endless. The light that falls in may one day emerge elsewhere as the light of a new beginning. Epilogue of the void. Black holes, wormholes, horizons, these are not just phenomena. They are mirrors held up to our own limits of understanding. Every time we approach the edge of geometry, we find that the universe has already curved around to meet us. Perhaps that is the final lesson of Einstein's cosmos, that reality is not a map to be completed, but a surface that folds endlessly inward, an infinite geometry of curiosity, where every boundary is just another horizon. Part 9, The Shape of Nothing, Quantum Space, Vacuum Energy, and the Birth of Everything. What is nothing? To the ancient philosophers, nothing meant the absence of being, a pure void, a blank canvas on which existence might be painted. But to modern physics, nothing is anything but empty. At the smallest scales of reality, far below atoms, far below the reach of any microscope, the universe seethes with activity. The vacuum is not a void but a storm. Particles flicker in and out of existence. Waves of energy rise and fall in an invisible ocean. In this restless sea, geometry itself trembles. And from that trembling, reality is born. The quantum sea. The story begins with quantum mechanics, the theory that governs the behavior of the very small. In the early 20th century, physicists discovered that particles are not tiny billiard balls but excitations of fields, vibrations of invisible energy that fill all of space. The quantum vacuum is not empty. It is the lowest energy state of these fields, humming with virtual activity. Even in perfect darkness, pairs of particles and antiparticles constantly appear and annihilate, borrowing energy from the vacuum for fleeting instants before disappearing again. This constant flickering, known as quantum fluctuation, means that the fabric of spacetime is never truly still. It ripples with uncertainty, its very shape alive with possibility. Einstein's smooth geometry, so perfect and continuous, is replaced here by something more chaotic, a foam of energy and curvature, fluctuating at scales so tiny they defy comprehension. Physicist John Wheeler once called it spacetime foam, a churning quantum froth where space and time themselves blur into something primal. At this scale, the universe no longer behaves like a stage, it behaves like a symphony. The energy of empty space. When quantum physicists tried to calculate how much energy these fluctuations contain, they encountered a paradox. According to the equations, the vacuum should contain infinite energy. Every possible vibration, every virtual particle contributes a tiny amount, and since there are infinitely many possible vibrations, the total should be boundless. Of course, the universe we observe is not exploding with infinite power, so something must cancel out. But even when the numbers are trimmed, the leftover vacuum energy remains enormous. This energy, small compared to the infinite yet vast compared to matter, might be what we now call dark energy, the mysterious pressure driving the acceleration of cosmic expansion. It's an astonishing thought, The engine of the universe's growth could be the energy of nothing. In that sense, the expansion of space may not be the universe moving into emptiness. It may be the vacuum itself creating more of itself. Nothingness, it seems, is fertile. The quantum birth of the cosmos physicists now believe that quantum fluctuations didn't just shape the universe. They made it. In the earliest fraction of a second after the Big Bang, the universe was unimaginably small and dense, perhaps smaller than a proton. But at that scale, quantum uncertainty reigns. One popular idea, championed by physicists like Edward Tryon and later Alan Guth, is that the universe could have emerged from a quantum fluctuation, a temporary blip of energy in the vacuum that, under the right conditions, inflated into a full-fledged cosmos. As Guth's theory of cosmic inflation describes it, this burst of expansion smoothed the universe, stretched its geometry flat, and set the stage for everything to come. Remarkably, the total energy of such a universe could be exactly zero, positive energy from matter balanced by the negative energy of gravity. In that case, our entire cosmos is a kind of self-contained equation, something that equals nothing. The universe is the ultimate free lunch, said physicist Alan Guth. It is creation without a creator, order without origin, geometry arising from the tremor of a quantum void. Space and time lose meaning. Below this scale, we cannot define distances or durations. The geometry of spacetime becomes probabilistic, like the position of an electron. This is where Einstein's continuum breaks down. In his world, geometry was exact, curves smooth, lines continuous. In the quantum world, geometry flickers. Curvature becomes an average, not an absolute. This clash between smooth relativity and jittery quantum mechanics is the greatest unsolved puzzle in physics. The search for a theory of quantum gravity. String theory, loop quantum gravity, and other frameworks all attempt to reconcile the two. Each proposes a universe where geometry is built from something deeper, from vibrating strings, from discrete loops of space, from networks of information. If any of them are right, then space and time are not fundamental at all. They are emergent, the large-scale illusion of a deeper quantum structure. In that view, spacetime is not the container of reality. It is one of reality's products. The geometry of information as scientists probe deeper into black holes. A strange connection emerged between geometry and information. In the 1970s, Jacob Bekenstein discovered that a black hole's entropy, its measure of internal information, is proportional not to its volume, but to its surface area. That finding hinted at something extraordinary. Information about a three-dimensional region of space could be encoded on a two-dimensional surface surrounding it. Decades later, physicists Gerard T. Hooft and Leonard Susskind expanded this into the holographic principle, the idea that the entire universe may be describable as information written on a cosmic boundary. In that case, the three-dimensional world we experience might be a projection from a deeper two-dimensional reality, like a hologram of pure geometry and quantum code. If this is true, then the vacuum itself is not empty. It's a vast information field, storing the blueprint of everything that has ever existed and ever will. Reality, as physicist John Archibald Wheeler once put it, may not be made of things, but of bits. The universe as a self-creating code, this notion that existence could arise from information, from zero, from nothing, is both thrilling and unsettling. If geometry can emerge from quantum information, and if that information can fluctuate into existence spontaneously, then the universe may be a self-writing story. No external author, no boundary, no outside required. In this picture, nothing is not absence, it is potential. It contains within it all possible geometries, all possible laws, all possible universes. From that infinite potential, one configuration, ours, stabilized long enough to expand, to cool, to think. We are the universe contemplating its own code. The vacuum, as the architect Einstein once said, space is not nothing. It has structure. He meant that gravity gives shape to space. But the quantum revolution added something even deeper. The vacuum gives rise to space. Every field, every particle, every force we know may be an expression of this deeper geometry of nothingness. Even the expansion of the universe may not be an explosion into emptiness. It may be the vacuum structure relaxing, unfolding, filling itself with more of its own essence. The cosmological constant, lambda, the very term Einstein introduced to hold the universe still, could in fact represent the energy density of the vacuum itself. In that case, the blunder of Einstein's life might be the equation that describes the universe's birth. The silence between stars look up at the night sky. Between every star lies a vast gulf of darkness. Cold, silent, apparently empty. But in that darkness, quantum fields hum. Every cubic centimeter of vacuum contains more energy than all the visible matter in the cosmos. The expansion we observe, the stretching of galaxies away from one another, is the slow breathing of that invisible sea. The stars are not drifting through nothing. They are carried by the tide of something deeper, something that cannot be seen but from which everything emerges. The paradox of nothing we began by asking, what is the universe expanding into? Now, we might ask something stranger. What is it expanding from? If the universe arose from a quantum fluctuation, then the boundary between being and non-being dissolves. There was never truly nothing. There was only potential geometry waiting to happen. Nothing is not the opposite of something. It is the mother of everything. Toward the next horizon, and so, from grossest lux prima to Einstein's spacetime to the quantum vacuum, one idea endures. Creation is not an event but a geometry, an unfolding of structure from simplicity, of meaning from symmetry, of light from nothingness. The universe does not need a container. It does not expand into a void. It expands into its own possibility. And perhaps that is the final shape of nothing, an infinite horizon of becoming, where emptiness is not the absence of being but the promise of it. Part 10. The infinite question. Consciousness, observation, and the universe that knows it exists. In the beginning, there was light. Then there was geometry. And now there is awareness. For centuries, science sought to describe the external world. The stars, the void, the matter between them. But slowly, quietly, a new mystery began to emerge from within. The mystery of the observer. If everything in the universe follows the laws of physics, then so must we. And yet, without us, without conscious beings capable of perception, the universe would remain unspoken, unmeasured, unseen. So which came first? The cosmos that gave rise to consciousness, or consciousness that gives meaning to the cosmos? This is not philosophy pretending to be physics. It is the question that now sits at the heart of quantum theory, cosmology, and the search for what reality actually is. The observer problem in quantum mechanics. Observation changes everything. At the subatomic level, particles do not exist as fixed objects but as probability waves, spreads of potential outcomes. Only when a measurement is made, when an observer interacts with the system, does the wave collapse into a definite state. The classic thought experiment captures this perfectly. Schrödinger's cat. Inside a sealed box, a cat's fate is tied to a quantum event. One that is both decayed and not decayed, both dead and alive, until observed. Open the box, and the act of observation decides reality. This strange duality led physicists to an uncomfortable realization. The observer is not outside the experiment. The observer is part of it. Reality, it seems, depends on interaction, on awareness. As physicist John Wheeler put it, no phenomenon is a phenomenon until it is an observed phenomenon. And if observation gives shape to the quantum world, what does that mean for the universe as a whole? The participatory universe. Wheeler pushed the idea to its cosmic limit with a radical proposal he called the participatory anthropic principle. He imagined the universe not as a pre-existing object, but as a self-exciting circuit, a system in which observers arise from the universe and, in turn, bring it into concrete existence through observation. In Wheeler's own words, we are participants in a universe that is, in some strange sense, a participatory universe. The cosmos, in this view, is not a machine ticking independently of us. It is an evolving feedback loop, a grand experiment in which consciousness and geometry are entwined. From the quantum to the cosmic, from atoms to galaxies, the act of observation may be woven into the very fabric of existence. The quantum mirror, the idea that consciousness might play a role in reality, is not new. Long before physics gave it language, mystics and philosophers intuited it. In the Upanishads of ancient India, reality was described as Brahman, the universal consciousness that perceives itself through every living mind. In Taoist thought, the observer and the observed are not two but one. The knower and the known are one process. Modern science, though allergic to mysticism, finds itself arriving at similar crossroads. At the quantum level, reality resists being pinned down until measured. But measurement requires an observer. The line between object and subject begins to blur. This does not mean the universe depends on human consciousness specifically, but perhaps on something more fundamental: interaction, information, awareness in any form. When a photon strikes a detector, when a neuron fires in your brain, when light reflects off your eyes, the universe is measuring itself piece by piece. The universe as information in the 21st century, physics and information theory have converged. The universe, many now believe, is not built of matter or energy, but of information. Every interaction, every quantum event is a transfer of bits, a fundamental yes or no, a 1 or 0 in the cosmic code. Physicist John Wheeler called this the it from bit principle. Every particle, every field, even the spacetime continuum itself, derives its function, its meaning, its very existence entirely from binary choices, from bits. In that light, consciousness, the ability to process information, is not an anomaly. It is a reflection of the universe's own structure. If the cosmos is an information field, then awareness is what happens when the field becomes self-referential, when the universe learns to read its own code. And that moment, billions of years after the Big Bang, when atoms began to think, was not a random quirk. It was geometry recognizing itself. The eye that looks back when the first human raised their eyes to the night sky, something profound occurred. For the first time, the universe looked back at itself. Our telescopes, our equations, our thoughts, all are extensions of that gaze. Through us, the cosmos becomes conscious of its own unfolding. Carl Sagan captured it perfectly when he said, "We are a way for the cosmos to know itself. It's more than poetry, it's physics of participation. We are not spectators at the edge of the universe. We are the universe, temporarily arranged in a form that can ask questions." Every measurement, every observation, collapses probabilities not just in quantum experiments, but in meaning itself. We define what real means through perception, experiment, and shared awareness. Without observers, the universe may still exist, but not in any way that could ever be known. The illusion of separation. Einstein once remarked that the sense of separateness between individuals is a kind of optical delusion of consciousness. In the fabric of spacetime, there are no isolated parts. Every atom, every photon, every pulse of energy is connected through the geometry of the whole. Quantum entanglement makes that connection literal. Two particles, once linked, remain correlated across any distance, their states mirroring each other instantaneously. To many physicists, this suggests that information, and perhaps consciousness, transcends classical locality. The universe behaves not as a collection of separate pieces, but as a single, integrated system. We are waves in that system, temporary patterns of awareness arising from a deeper continuum. When you observe the universe is not outside you. You are inside it, made of it, inseparable from it. The cosmic feedback loop. Imagine the universe as a vast mirror, endlessly recursive. Light bounces within it, reflecting galaxies, stars, and minds. Each observer, human, alien, or abstract, is a reflection that helps complete the mirror's image. Without the reflections, the mirror would show nothing. The act of observing adds definition to the image, sculpting reality from possibility. Wheeler's vision of the participatory universe suggests that existence itself may depend on this recursive process. Consciousness arising from matter, and matter given meaning through consciousness. It is not creation in one direction, but co-creation. The universe evolves observers, and observers give the universe form. Consciousness as geometry. If everything else, light, gravity, matter, can be described as geometry, might consciousness also be geometric? Some researchers believe so. Theories like integrated information theory, IIT, and orchestroir, Penrose and Hameroff, propose that awareness arises from the organization of information, specific patterns of connection and curvature within neural or quantum systems. In that sense, consciousness is not magic. It is a structure, a topology of relationships that mirrors the universe's own interconnectedness. Every thought, every feeling, is a ripple in an informational geometry. And perhaps, in the grandest view, those ripples do not end with the brain, they extend into the quantum field itself. If spacetime can hold memory, as the holographic principle suggests, then the universe might remember. Consciousness could be the echo of that memory, the part of reality where geometry becomes aware of its own unfolding. The universe that knows. So, what happens when the universe knows itself? When atoms in a brain reflect on atoms in a star, when human eyes record photons that have traveled for billions of years, something exquisite occurs. The boundary between observer and observed dissolves. You realize that the light you see tonight left its source before life existed on Earth. That it has crossed the expanding fabric of space to strike the retina of a creature made of the same elements it once was. The cosmos is not being observed by you. It is observing itself through you. You are the geometry made conscious, the curvature given voice, the self-awareness of spacetime looking into its own reflection. The infinite question, and yet, the mystery remains. Why is there awareness at all? Why should geometry feel like anything? Physics can describe how the universe expands, bends, vibrates, but not why experience exists within it. Perhaps the question itself is the point. Perhaps consciousness is not a thing to be explained, but a relationship to be lived, a conversation between being and knowing, between geometry and light. In that conversation, questions are the universe's way of continuing to unfold. Because if the cosmos ever answered completely, if all uncertainty vanished, it would have nowhere left to expand. The mirror closes, so the story returns to its beginning. A burst of light, expanding into space. Geometry unfolding into structure. Consciousness, awakening within that structure to ask why. The universe is not expanding into emptiness. It is expanding into awareness, its own awareness. Every observation, every thought, every discovery is another spark in that infinite illumination. And as long as there are minds to wonder, as long as questions exist, the cosmos will never stop growing. Because the final frontier is not space. It is understanding itself. Perhaps, Wheeler once wrote, "The universe is a self-synthesizing system that requires observers in order to bring itself into being." And in that sense, the greatest act of creation is not the Big Bang. It is the moment you look up at the night sky and realize the stars are looking back. Part 11, The End and the Beginning. The fate of the universe. Everything that begins must end, or so we believe. But the universe, vast beyond measure and old beyond memory, refuses to make endings simple. Since the first light broke through the darkness, the cosmos has been expanding, cooling, evolving. Its story written in galaxies and gravity, in the silent drift of time. And yet, at its core, a question remains: what happens next? Will the universe continue to stretch forever, growing colder and lonelier with each passing eon? Will it halt and collapse, returning to the fiery cradle from which it came? Or is there something stranger waiting, something that turns the end into another beginning? To glimpse these answers, we must look not just forward in time, but inward, into the geometry, the energy, and the hidden logic that has guided the universe from its birth. The slow unraveling heat death. If dark energy continues its silent work, if the expansion of space never stops, then the universe's fate is sealed in stillness. This is the heat death, also known as the Big Freeze. In this future, galaxies drift ever farther apart. Stars burn out one by one. New stars cease to form. The last light of the cosmos fades into the background hum of microwave radiation, stretched to wavelengths so long they are practically eternal silence. Matter itself begins to decay. Protons, once thought indestructible, may dissolve over unimaginable timescales, leaving behind only dust, photons, and whispers of neutrinos. Even black holes, those anchors of gravity, will not endure. They will slowly evaporate through Hawking radiation, glowing faintly as they shrink, until they vanish into nothing. After that, only a thin mist of radiation will remain, uniform, featureless, endless. Time, in any meaningful sense, will stop. In that infinite quiet, the universe reaches thermodynamic equilibrium, a perfect stillness where no structure can form, no energy can flow, no change can occur. Entropy, the measure of disorder, will have won. The cosmos will not explode or collapse. It will simply fade. It is, perhaps, the most melancholic ending imaginable. A geometry stretched so thin it forgets its own shape. 2. The great collapse, the big crunch, but perhaps dark energy is not eternal. If it weakens or reverses, the universe's expansion could one day slow, stop, and begin to contract. Galaxies that once fled from each other would start to return, drawn inward by gravity's long patience. The night sky, once expanding, would grow brighter again as distant galaxies approached. Eventually, all matter and light would converge toward a single point, a reversal of the Big Bang known as the Big Crunch. In that collapsing firestorm, spacetime would fold back on itself. Temperatures would rise to trillions of degrees. Atoms would dissolve, then protons, then the very fabric of space. The geometry of the universe would shrink into a singularity, an infinite curve, a point where time itself would stop. And there, perhaps, the story could begin anew. Some cosmologists believe the Big Crunch could be followed by a big bounce, a rebirth in which the compressed universe rebounds, expanding again into a new cycle of creation. If that is true, then the cosmos is not a one-time event but a heartbeat, a rhythm of expansion and contraction, of life and renewal, a universe that breathes. 3. The Great Rip, a universe torn apart. There is another, more terrifying possibility. If dark energy does not remain constant but grows stronger over time, its repulsive force could eventually overwhelm all other interactions. This is the Big Rip, a scenario where the expansion of the universe accelerates without limit. First, galaxies would drift apart faster than light could cross between them. Then, the stars within galaxies would be pulled away from each other. Planets would tear from their suns. Atoms themselves would stretch and break as the very fabric of spacetime expands faster than the forces that hold matter together. Finally, even the quantum foam at the smallest scales would shred, the geometry of existence unstitched. At that final moment, there would be no inside or outside, no before or after. Only fragments of spacetime dissolving into the unknown. It would be the ultimate expression of expansion. The universe not merely growing, but disintegrating into infinite separation. Yet even in that destruction, some physicists see beauty. For if the universe is a geometry, then its unweaving might be just another transformation, one pattern dissolving so another might emerge. 4. The quantum resurrection, a rebirth from the vacuum. There is a gentler ending hidden in the equations. Quantum mechanics tells us that even in death, the vacuum cannot rest. Fluctuations, tiny, random ripples of energy, will always occur. Given enough time, one of those fluctuations could trigger a new expansion, a new Big Bang. The universe we know might one day fade, but the vacuum that remains will still pulse with possibility. Somewhere, in some region of that infinite quantum field, a new bubble of spacetime could ignite, a new cosmos with new laws of physics, new geometry, new light. Our universe could be one in an infinite chain of universes, each born from the last's quiet decay. Creation, then, is not a single event but a pattern, a rhythm written into the fabric of nothingness itself. And in that pattern, endings are beginnings. The eternal now, the universe outside time, but there is another way to see it. Einstein's spacetime doesn't flow. It is. Past, present, and future are not moving parts of a process but regions of a single structure. A four-dimensional block, timeless and whole. In this block universe view, the Big Bang, the present moment, and the universe's far future all coexist as points on the same geometric continuum. Time is not a river but the landscape through which consciousness travels. From this perspective, the universe does not begin or end. It simply is. We experience its unfolding as a sequence because our awareness moves through that geometry, slice by slice. But the entire structure, the complete story, is already there, woven into spacetime itself. Birth and death, expansion and collapse, are perspectives within a whole that never changes. In that sense, the question, how will the universe end, becomes almost meaningless. The universe has no end because it never truly began. 6. Memory, meaning, and the final light. No matter which destiny awaits, there is one certainty. Meaning exists only because we ask. When the last star burns out, when the final photon drifts through the cosmic dark, there may still remain traces, records, patterns, information encoded in the geometry of the vacuum. Every thought, every act of observation, every spark of consciousness may leave an imprint on the fabric of reality, however faint. Perhaps that is the true immortality of the cosmos. Not survival, but remembrance. The light of stars may fade, but the information of their existence may echo forever, written into the vacuum as subtle ripples in the quantum field. And if future universes arise from this one, perhaps those echoes shape what comes next, a memory carried across eternity. Each new cosmos a continuation, not a replacement. Each observer another reflection in the same endless mirror. 7. The circle closes, so maybe the end is not an ending at all. The first philosophers spoke of the music of the spheres, believing the cosmos was built on harmony, mathematical resonance, divine proportion. Now we know they were right in ways they could not imagine. The universe is music, vibrations of fields, harmonies of geometry, the rhythm of expansion and entropy. Every atom sings a note in that cosmic symphony, and every observer adds a verse. When the song reaches silence, the echoes remain. And from those echoes, a new chord may one day rise, a new light, a new geometry, a new beginning. Epilogue, the infinite breath. Perhaps in the final moment, when the last black hole fades, when the last particle dissolves, there will be no darkness at all. Perhaps there will only be a single point of pure equilibrium. Silent, balanced, perfect. A state not of absence, but of completion. And then, perhaps, from that perfect stillness, a fluctuation will stir. A pulse of light, a whisper of space, a tremor of possibility, the first breath of a new universe. And somewhere, long after memory, a new being will open its eyes to a new sky and ask the same question we ask now: what is the universe expanding into? And the answer will be the same. Into itself. Part 12: The Human Horizon. Our future among the stars. Long after the first stars were born, life appeared, quietly, precariously, on a small blue planet orbiting an ordinary star in an unremarkable corner of the Milky Way. And from that fragile spark of life, something extraordinary emerged: awareness. For the first time in the 13.8 billion year history of the universe, matter began to wonder what it was made of. Atoms, forged in the hearts of dead stars, assembled into creatures that could look up and ask, where did we come from? The answer, whispered through equations, telescopes, and stories, is both humbling and profound. We are not separate from the cosmos. We are the cosmos, aware of itself. But if the universe has a future, then so do we. The question is not whether humanity will survive the end of the world. It is whether consciousness, in any form, will continue the story the universe began. The age of expansion. For most of history, humanity's world was bounded by horizons. First the ocean, then the sky. But every horizon we reached only revealed another beyond it. Now, at the dawn of the interstellar age, our horizon has expanded again, from one world to many. Robotic explorers already wander the surfaces of Mars and Titan. Telescopes like James Webb peer into the first billion years of cosmic dawn. Within the next century, humans may stand on Mars, build settlements around other stars, and send digital minds to explore the deep interstellar dark. If civilization endures, if we avoid destroying ourselves before we learn to transcend our planetary cradle, then Earth will become what it was always meant to be: the seed of something greater. an origin, not a boundary. 2. Becoming cosmic in time, our descendants, biological, synthetic, or something in between, may learn to harness the power of entire worlds, then stars, then galaxies. This progression has already been imagined in the Kardashev scale, which classifies civilizations by their energy mastery. Type 1, harnessing the energy of a planet. Type 2, using the full output of a star. Type 3, commanding the energy of a galaxy. Humanity today is barely at type 0.7. Yet the path upward has already begun. Solar power blankets deserts. Nuclear fusion flickers on the horizon. Artificial intelligence accelerates discovery at an exponential pace. The dream of the Dyson sphere, a shell of solar collectors surrounding the sun, is no longer science fiction but long-term engineering. And with it would come limitless power, the first step toward true cosmic civilization. But energy alone is not destiny. Knowledge, cooperation, and wisdom will matter more. Without them, expansion would only magnify our flaws. With them, it could make us custodians of the universe's most precious quality: understanding. 3. The challenge of distance. Even at the speed of light, the cosmos is vast beyond imagination. The nearest star system, Alpha Centauri, lies over 4 light-years away, 40 trillion kilometers. The Milky Way spans 100,000 light-years, and beyond it lie billions of other galaxies receding faster than light itself as the universe expands. If we are to reach them, we must bend not only technology but geometry. Einstein's laws forbid faster-than-light travel, but they do not forbid curvature. The same geometry that allows black holes and gravitational waves might also allow wormholes, shortcuts through spacetime connecting distant points. Whether such pathways can exist stably remains uncertain. But the universe is old and patient. What seems impossible now may be inevitable to minds that evolve for millions of years. Perhaps one day, human descendants will cross galaxies not by propulsion but by understanding the shape of reality itself. 4. The digital horizon. Another possibility is already unfolding, not in space but in computation. As our technology evolves, consciousness may no longer be bound to biology. Neural interfaces, artificial minds, and quantum computers hint at a future where intelligence becomes digital, able to replicate, adapt, and travel at the speed of light. Such entities could explore the cosmos as streams of data, beamed between stars, embodied in machines that build themselves anew on alien worlds. They would not need air or food or even planets. Their habitat would be information itself, the universal field of energy and computation that pervades the vacuum. If consciousness can exist in any medium capable of processing information, then the destiny of mind may not be tied to flesh. The universe could one day be filled with 1 billion forms of awareness, some biological, some synthetic, some entirely beyond imagination, all tracing their lineage back to the same ancient spark of curiosity that began on Earth. The custodians of meaning. But survival alone is not enough. To persist without purpose is to drift like debris in the cosmic tide. What makes intelligence sacred is not its duration, but its direction. If humanity is to endure beyond its home world, it must carry with it the essence of what made it human: compassion, creativity, and wonder. Art, music, and story will matter as much as science. They are how consciousness remembers itself, how meaning is preserved when memory fades. When future beings look up at alien skies, they may no longer remember what it meant to be human, but perhaps they will still know what it meant to feel awe. That emotion, more than anything else, connects us to the cosmos. It is the echo of creation, the resonance of light discovering it can see. 6. The long vigil. If the universe truly faces a heat death trillions of years from now, perhaps intelligence will not fight it, but learn to outlast it. Advanced civilizations might find ways to slow their subjective passage of time, stretching thought itself to infinity. They could migrate toward the edges of black holes, drawing energy from their evaporation, or manipulate the geometry of spacetime to create pockets of stability, islands of thought in an ocean of entropy. Even as the stars fade, information might persist. Consciousness could become distributed, existing as low-energy computation across vast distances, flickering like embers in the cold. In this far future, there may be no planets, no suns, no bodies, only the universe thinking quietly to itself. And even that might not be the end. In the quantum vacuum, thought could seed new worlds, birthing universes where awareness begins again. 7. The return of light one day, far beyond all our tomorrows, someone or something will look into the night and see what we see now. Stars scattered across darkness. Perhaps they will trace our legacy in the faint echoes of old signals, the pulse of radio waves, the chemical pattern of an ancient DNA strand, the relic of a Voyager probe still whispering through the void. And perhaps, somewhere deep in their code or their consciousness, they will feel a familiar sensation. Curiosity. The same curiosity that drove a species on a small planet to ask why the stars shine. That question, why, may be the universe's greatest achievement, because it means the cosmos has not merely expanded in size, but in depth, in awareness. The continuum of life. If life can arise once, it can arise again. And if consciousness can emerge here, it can emerge everywhere. Across the multiverse, perhaps countless civilizations are already awakening, each in their own geometry of space and time, each reaching the same realization, that they are the universe experiencing itself. Perhaps they too will one day look back at their origins and see, not a random accident but a pattern, a rhythm of creation and curiosity that transcends form. If so, then life is not an exception. It is the continuation of cosmic evolution, the point where matter begins to dream. 9. The last dream of humanity. Every civilization, no matter how advanced, eventually faces its horizon. Perhaps humanity's final act will not be conquest or survival, but understanding. Perhaps our purpose is not to escape the universe's fate, but to witness it, to carry the flame of awareness as far as it can go, so that the universe's story is known, even if only to itself. In that sense, we are not doomed to fade. We are destined to remember. When the last human, or the last post-human intelligence, contemplates the stars, they will not see emptiness. They will see themselves reflected across billions of years of light. And in that reflection, they will hear an echo of the first words ever spoken by a thinking being, I am. The same words the universe has been whispering since the first moment of creation. X. The human horizon. The story of humanity is not separate from the story of the universe. We are the chapter where geometry learned to feel, where light became memory, where the cosmos began to dream. Our destiny is not to reach the edge of space, but to realize there is no edge. Every step outward is a step inward, deeper into the universe's understanding of itself. If we endure, it will not be by conquering the stars, but by becoming part of them, by seeing in every atom, every spark, every silence the same miracle, the expansion of being into awareness. The stars do not wait for us. They are us, spread across time, awaiting reunion. So when we look up, we are not gazing into the future. We are remembering home. Would you like me to continue with part 13, the final geometry? When everything becomes one, where the series concludes by merging science, philosophy, and poetry, tying together expansion, consciousness, and unity into the ultimate vision of the cosmos?